Okay, I got cut off right before I wanted to end last time. What we were talking about is the relationship between elementary charge and coulomb. A coulomb is a huge number of elementary charges, 6.25 times 10 to the 18th. Therefore, an elementary charge is a tiny fraction of a coulomb, 1.6 times 10 to the negative 19th of a coulomb. If this is a little bit confusing to you, what I would suggest doing is thinking of it in the following way. I've got a big circle here and a bunch of little tiny circles on the inside. Think of the little tiny circles as electrons or elementary charges. Each one of the little circles is -1 elementary charges, or -1.6 times 10 to the negative 19th coulombs. Okay, a tiny, tiny amount of a coulomb. The big circle, on the other hand, is a coulomb. It's a large collection of electrons. It is 6.25 times 10 to the 18th electrons. I have that negative there to remind us that it's negative, or -1 coulombs. Okay? Make sure you understand the difference between a coulomb and an elementary charge. An elementary charge is just one electron or proton. A coulomb of charge is many, 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 many electrons or protons. Okay, let's go to the back. So, we know that there are almost untold numbers of electrons and protons making up everything that we see around us. Thankfully for us, this is usually the charge on an object, any large object, is usually kept electrically neutral. Okay? And what that means is not that it's not made up of protons and electrons. Obviously, everything is made up of protons and electrons. Electrically neutral. Oh, do I have this up too high? Yes, I do. There we go. Okay. So it's not that it's not that large objects aren't made up of protons and neutrons. It's instead, what this means that most electrons most large objects are electrically neutral because they have equal numbers of protons and electrons. Okay, so large objects are anything, you're talking about basically like any object larger than, an atom or a molecule. Most of them have equal numbers of protons and electrons. Take this pen, for instance. This pen has, I don't even want to estimate how many protons and electrons are inside of this pen. However, the number of protons is approximately equal to the number of electrons. It's got to be extremely close to equal, if not exactly equal, because this has no noticeable electric charge to it. Okay? Now, I say most large objects are electrically neutral. That doesn't mean that it's impossible for a large object to have a charge or a net charge. Because occasionally, remember what type of charge can move? Electrons, the negative charges. Occasionally, they can be transferred to or taken away from an object. You can either put more electrons on that object or take away electrons. That leaves it with what we call a net charge. Remember what the word net means. Net just means like overall, or the sum of. A net charge does not tell you how many electrons or protons are on the object. Instead, it simply tells you how much extra charge of one type there is. So, the example I like to give, and usually I like to do this more in the winter because it's very noticeable in the winter, but we'll have to make do with it for right now, is combing your hair, okay? So here's a comb. Here's all the little teeth on the comb. Maybe I should have drawn this before. It's fine. Okay. You guys get to see all my non-existent arts and crafts skill. So there's a comb. And let's say I'm just going to symbolize electrons and protons as plus and minus signs. So I'm going to do this. Plus, minus, plus, minus, plus, minus, plus, minus. Okay? Now, the pluses are positives. Those are protons. The negatives are electrons, the minus signs. Okay? Obviously, there's many, many more than this, but we're just trying to show an example. I have 4 positive charges, 4 protons, 4 negative charges, 4 electrons. The net charge is 0. Okay? 4 positives plus 4 negatives, that cancels out. Okay, each one of the positives or protons has a negative charge, an electron, to kind of cancel out the bigger effect of that charge. Now you really get to see my lack of drawing talent. Okay, there's a person. That's about all I can do for a nose. They're going to be smiling. It's a pretty terrible looking smile. We got some ears, and they got some hair. Maybe not enough to warrant a comb, but whatever. Okay, and let's say that this person, again, has 4 positive charges and 4 negative charges. Okay, their net charge would also be 0 E. Now, what if they interact? Okay, what if that comb interacts with the person's head? Okay, so what actually happens, and you might notice this, those of you who comb your heads in the winter, is that you start to see the effects and you would say, oh, it's static electricity. It's causing my hair to stand up a little bit more, right? This is not a unfamiliar phenomenon to you guys. But what might happen here is that the comb actually pulls some electrons away. Now, how would I show this? The comb pulling electrons away. Well, remember, the positive charges are the protons. They're locked in place. They can't really move. Okay? They are stuck in the nucleus. So whenever I do these drawings where I'm showing charges moving from one place to the next, I'm never going to move the positives around. I'm only going to move the negatives around. The comb pulls some electrons away. So we're going to keep the positives in the places that they already were from my previous pictures. Okay, that positive's on his head. And here we go. Now what can happen is the comb can pull some electrons away. That means that this guy is left with not as many electrons on his head, just those 2. The other electrons might have gone onto the comb. Okay, I'm going to draw a line so we can separate the comb from the guy. So, if we're looking for the net charge on the comb now, because the comb took those electrons away, remember that can happen, electrons can move between objects. The comb took some of those electrons, it gained electrons, the comb should have a negative charge. We now have 1, 2, 3, 4, 5, 6 negatives or electrons represented on the comb, and only 4 positives. The comb's net charge is now negative 2 elementary charges. On the head, we have 1, 2, 3, 4 positive charges representing protons, but only 2 negative charges representing electrons. The head's charge is positive 2 E. Interesting. Okay, so the comb gained the electrons that the head lost. The comb now has a charge of negative 2e. The head has a charge of positive 2e. And again, like I said, obviously these objects are made up of more than 4 protons and electrons for each object. I'm just trying to simplify here. Okay, we're trying to make this as easy as possible with small numbers so we can understand. Let's do another example. Let's say you have a neutral piece of Scotch tape and it's placed on a desk and it's peeled off. You can actually do this at home, taking with it 6.2 times 10 to the 13th electrons. What are the new charges on the tape and the desk? And by the way, we want this in coulombs. Okay, so what we know is that the tape took 6.2 times 10 to the 13th electrons with it. So tape gains 6.2 times 10 to the 13th electrons. It doesn't gain any protons. Remember, the protons do not move. The protons are locked in place in the nucleus. Where did it gain those electrons from? They didn't just appear out of thin air. The desk must have lost the same amount. And if the tape gained those electrons, remember, gain electrons means it becomes negative because electrons themselves are negative. The desk lost some electrons. The desk now becomes positive. Okay? If we want to know the new charges in coulombs, all we have to do is unit conversion, because we know the conversion between elementary charges. Okay, 6.2 times 10 to the 13th E means 6.2 times 10 to the 13th electrons. We know the conversion is one elementary charge is equal to 1.6 times 10 to the negative 19th coulombs. This is just unit conversion. If you were sketchy on unit conversion in the beginning of the year, now is the time to definitely learn it, okay? Otherwise, you will get some of these questions wrong because you'll use the wrong conversion. The reason I have it set up like this is the number I have to start with. I have this many elementary charges. I want to convert that number into coulombs. I want to know how many coulombs this amount of elementary charges is. I set up my parentheses with my fraction. 1e, that's one elementary charge. Elementary charge goes on the bottom in this case because I want to cancel out those units. And so I write the corresponding number of coulombs on top. And now I simply do the math. If you were multiplying a number by a fraction, you would multiply the numerator by the numerator, the denominator by the denominator. The denominator here is just 1, okay? 1 times 1 is just going to give you the same thing. 6.2 e 13 times 1.6 e negative 19. And what I end up with is a number that is very, very small, okay? It's not a full coulomb. And if I do, let's see, 1, 2, 3, 4, 5, 6. 9.92 times 10 to the negative 6th coulombs. We know it's negative 6 because it's a very small number. Okay? That's still not my final answer. Remember, the tape just has this many more electrons. So the tape is now negative. So the tape's new charge is negative 9.92 times 10 to the negative 6th coulombs. What about the desk? The desk has a charge of positive because it lost those charges. 9.92 times 10 to the negative 6th coulombs. We had a neutral piece of Scotch tape and a neutral desk. Originally, there were the same amount of protons and electrons on both objects. Now, we still have in combination, if you were to add the charges of those two objects, it's still neutral. But one object is now negative, one object is now positive. So the key here is that objects lose. One object loses as many electrons as the other object gains. That's how this always works. I've got a couple more examples here and then we're done. Let's say we have 4 objects have acquired different net negative charges. How many more electrons than protons does each object have? What this is asking us to do is to find the net charge in elementary charges. We already have the net charges in coulombs. We just need to convert from coulombs back to elementary charges. So we start with A, negative 8 times 10 to the negative 19th C. We write down the number we're given, 8 times 10 to the negative 8 times 10 to the 19th C. We set up our unit conversion. Okay, C is going to go on the bottom because that's what we want to cancel out. E is going to go on top. The conversion I like to use, you can use the other one, and matter of fact, probably you should test it out to make sure you get the same answer, is 1e over 1.6 times 10 to the negative 19th c. What this would give me is, let's see, I would multiply, so negative 8 times 10 to the negative 19th times 1 is just that number, divide it by 1.6 times 10 to the negative 19th. So, 8, negative 8, e, negative 19, divided by 1.6 e negative 19, I get a charge of negative 5e. What that means is that this object has 5 electrons in excess. Is 5 more protons than electrons. Not just 5 electrons, but 5 more electrons than protons. Hopefully, I think I said that the right way. Again, I can show you if you wanted to use the other conversion, 8e negative 19. Let's say you wanted to use 6.25 times 10 to the 18th e over 1c. That's fine. You would end up multiplying by 6.25 e18. You still get the same answer. Okay? That's why I say pick one way and get used to it. Okay? Pick one of those conversions. You don't need to know both of them. Both of them are on the reference tables for you. I'm going to do 2 more real quick, and then the third video I'm going to come to this one because that one's a little bit different. 2 more examples real quick. 2.56 times 10 to the negative 18th c. We're going to convert that. 1.6 times 10 to the negative 19th c. 1e. Cancel out the c's. 2.56 negative e negative 18 divided by 1.6 e negative 19. We get negative 16e. That means 16 extra electrons. And our last one, negative 1.28 times 10 to the negative 13th c. Matter of fact, you should predict right now, is this going to be a big number or a small number? We convert. Negative 800,000 e. 800,000 extra electrons. You know that that should be a bigger number because your amount of charge was bigger. We're going to do the last one when I come back, and then we'll finish up with this chart. We'll be done for today. Thanks.